In the world of AI, things move so fast that progress is measured in weeks, not years. And this week, a new model just dropped that isn't just another update, it's a fundamental shift. We're about to look at an AI that is absolutely tearing up the leaderboards and challenging the biggest names in the game.
Okay, just look at these charts. On some of the toughest AI benchmarks out there, a new challenger called GLM-5 is going head-to-head with the giants. We're talking Claude Opus, GPT 5.2, and it's winning. It doesn't matter if it's complex reasoning, browsing the web, or writing code, it is consistently a top performer. This isn't just a small step up, this is a new contender for the throne.
And here's what makes this chart a really big deal, historically speaking. On the AI index, which bundles together 10 super tough evaluations, GLM-5 is the very first open weights model to ever score a 50. Now what that means is its core design is publicly available. Unlike those closed proprietary models, it's now outperforming. That's huge.
But okay, benchmarks are one thing. What about the real world? Well, on LLM Arena, this is where thousands of people blindly vote on which AI response is actually better for real tasks. GLM-5 has been crowned the #1 open model, and that's for both general text and for writing code. So this isn't just about passing tests, it's about being genuinely incredibly useful to actual people.
So the name behind all this excitement is GLM-5. And as we're about to see, its incredible success isn't just because it's bigger. It's because it's fundamentally smarter in how it's designed. All right, so the wow is pretty clear, right? We have a new champion in the open weights world that's playing in the big leagues. But that just leads to an even bigger question. How does it actually do this? How can a model deliver this kind of top-tier performance without needing a ridiculous amount of computing power for every single thing it does? Well, the answer comes down to two key innovations.
And this brings us to the how. The secret to all this efficiency, it starts with a revolution deep down in the model's core architecture.
It's called Deep-Seek Sparse Attention, or DSA for short. Now that might sound complicated, but the core idea is actually simple, and frankly, it's brilliant. Instead of paying equal attention to every single piece of information it's given, the model learns to dynamically focus its brain power only on what's most relevant at that exact moment.
Think of it this way. The old method, that's called dense attention, is like trying to find one specific sentence in a book by rereading the entire book from cover to cover every single time. It's thorough, sure, but it's incredibly inefficient. The new way, sparse attention, is like using the table of contents and the index to jump straight to the right page. It's faster, it's smarter, and it's way, way more efficient.
And the impact of this is just staggering. Researchers discovered that with the old method, a full 90% of the calculations the AI was making were completely redundant. This new architecture lets the model just skip all that wasted effort without losing any understanding at all.
So what this means in practice is that GLM-5 can process enormous amounts of information. We're talking up to 128,000 tokens at roughly half the GPU cost of the older methods. But look, a smart architecture is only half the story. You also need a really smart education.
And this brings us to the second part of the how, a completely re-engineered training process. It's designed to create not just a database of knowledge, but a true problem solver.
As you can see from this pipeline, the model's training is this really carefully orchestrated journey. It starts on the left with pre-training, where it learns from a mind-blowing 27 trillion tokens of data. In the middle, mid-training extends its ability to handle really long documents. But the real magic? That happens all the way on the right, in the final post-training phase.
In post-training, the model basically goes through a 3-step curriculum. First, it masters pure reasoning, logic, math, and science problems. Then it learns to be agentic, how to use tools and plan out multi-step tasks. And finally, it gets polished to be a safe and helpful general assistant. It's a clear progression from pure logic to practical action.
And underpinning this whole process is a brand new, much more flexible training system. It lets the model work on multiple complex problems at the same time, learning from them continuously without all the slowdowns that used to plague the older methods. So we've seen the wow, and we've gotten a look at the how. Now it's time for the now. What does all this mean in the real world? Well, it signals the dawn of something called agentic engineering.
To see what this new agentic ability really looks like, researchers gave GLM-5 a crazy challenge: run a simulated vending machine business for an entire year. Now, this isn't a simple question-and-answer task. It requires long-term planning, managing resources, and making decisions day after day. And the result?
GLM-5 didn't just manage the business, it turned a final profit of over $4,000, outperforming every other open-source model they tested. This is a real, concrete demonstration of what long-horizon planning looks like in action.
And this is what agentic engineering is all about. It's this major shift away from just giving an AI a simple prompt and getting one answer back, what some people jokingly call vibe coding, and moving towards building an AI that can function as an autonomous agent, one that can plan, use tools, and tackle complex goals all on its own.
A key technique that makes this possible is called interleaved thinking. As you can see in this diagram, before the model takes any action or calls any tool, it actually generates its own reasoning. It thinks, then it acts, then it thinks again, then it acts again. This step-by-step reasoning process makes its behavior way more stable and reliable when it's working on really complex tasks.
This one quote from the research paper just captures the entire shift perfectly. We are moving from a world of vibe coding, where you kind of just hope the AI gets the gist of what you want, to agentic engineering, where you empower the AI to be a capable, autonomous partner. GLM-5, with its super efficient architecture and its agent-focused training, is a massive step in that direction. And it leaves us with a truly exciting question. If an AI can start to work with the kind of planning and tool-using capabilities of an engineer, what in the world is it going to be capable of building next?
You know, we've all been promised these incredible AI assistants that really get us. But let's be honest, most of the time they feel like they have total amnesia. Well, today we're looking at a new framework called Maple that might just be the cure, promising an AI that finally actually remembers you.
So picture this. We got Sarah, a senior machine learning engineer, and Marcus, who's a new product manager. They both ask their company's AI the exact same question. What's a transformer in AI? And what do they get? The exact same one-size-fits-none answer. Sarah's frustrated because she wanted code details. Marcus is just lost in all the jargon. The AI completely failed both of them.
And here's the part that'll make you want to tear your hair out. The system knew Sarah loves technical deep dives and code examples. It knew Marcus learns best with simple analogies. All that data from their past conversations was right there, stored away. The system just ignored it.
Which brings us to the big question, right? Why does this keep happening? Well, the folks behind the Maple framework say it's not a memory problem at all. It's an architecture problem. We've been thinking about this the wrong way from the very beginning.
Now, this is where it gets really interesting. The core idea behind Maple is that what we call memory isn't one single thing. Nope, it's actually three totally separate capabilities that we've been mistakenly lumping together. Let's break those down.
So first up, you've got memory itself, and you should just think of this as a giant warehouse. It's just the storage space. It holds all the raw data, every chat, every piece of feedback, every preference you've ever mentioned. It just sits there waiting.
Next, we have learning. This is like the smart curator of that warehouse. It's the intelligence that works quietly in the background, sifting through all that data to find the important patterns. This is the part that figures out, hey, Sarah always clicks on the code examples, or Marcus seems to really get these analogies.
And finally, we have personalization. This is your personal shopper. When you ask a question, this is the agent that sprints over to the curator, grabs the file of insights about you, and uses it in that moment to custom build a response that's perfect for you.
I love this analogy because it just makes so much sense. The warehouse stores everything, the curator figures out what's important, and the shopper grabs exactly what you need right when you need it. When you separate these jobs, the whole system becomes exponentially smarter.
So the billion-dollar question is, how do you actually build this separation into a system's DNA? Well, that's exactly what Maple is. It's an architecture designed from the ground up to treat these three components as their own distinct but coordinated agents. So here's how it plays out in real time. You ask a question. Instantly, the personalization agent zips over to memory and grabs what it knows about you. The main agent uses that context to give you a perfectly tailored answer. And then, and this is the genius part, after you have your answer, the learning agent gets to work in the background, analyzing that whole interaction to make your profile even richer for next time. And this diagram really shows you the secret sauce. See, your request is in the fast lane. It gets a personalized response lickety-split. The deep thinking, the part where the system actually gets smarter about you, that happens completely in the background, asynchronously. This is the key. The AI is constantly improving without ever making you wait. And here's the proof in the pudding. On the left, that's the generic junk Sarah and Marcus got before. But with Maple, Sarah gets a straight-up PyTorch code snippet, exactly what she needed. And Marcus gets this great analogy he can actually use. It's the same question, but the architecture delivers two wildly different and infinitely more helpful answers.
Okay, that all sounds fantastic in theory. But does this architectural shift actually deliver, when the rubber meets the road? Well, the researchers pitted Maple against a standard, stateless AI to find out.
And wow, the results are pretty stark. Just look at this. The old school AI, it only managed to use what it knew about the user less than half the time. But Maple, it nailed it, incorporating user traits in 75% of its answers. That's a massive leap. And it's not just that. A human judge also rated Maple's overall answers as being significantly better.
Let's just zero in on that quality score for a second. We're talking a 14.6% jump. Now, in the world of AI benchmarks, that's not just a little bump, that is huge. This isn't some minor tweak. It's proof that changing the core architecture delivers a major, meaningful leap in performance.
So how does it pull this off? Well, it's not about remembering just one little fact. Maple wins because it can synthesize multiple things about you. It understands you live in the city with kids and a dog, and connects that to a suggestion for durable furniture. It anticipates needs you didn't even state, like recommending an ergonomic chair because it remembers you mentioned a bad back months ago. It just stops asking you questions it should already know the answer to.
So let's zoom out for a second. Why is this so important? What does this mean for the future of AI? Well, it's about fundamentally changing how we approach building these intelligence systems.
A common idea right now is to just make the AI's short-term memory, its context window, bigger and bigger. But that's a dead end. You just end up with what the paper calls context rot, where old, irrelevant info clogs everything up. Maple's approach is completely different. The goal isn't bigger memory, it's smarter memory.
So, I'll just leave you with this thought. Imagine an AI that doesn't just respond to you, but anticipates you. An assistant that understands your goals, your style, your whole context. What could you create, what problems could you solve if your AI truly, deeply, actually knew you?
Okay, so you've seen the headlines, right? AI is writing code. It's going to automate all of software development. The hype is, well, it's everywhere. But what actually happens when you take these AI agents out of the pristine lab and throw them into the messy, real world of software engineering? Well, a new study did just that. And let me tell you, the results are a serious reality check.
So that leads us right to the big question, the one on everybody's mind. And look, we're not just talking about an AI that can spit out a few lines of code anymore. The new dream is for these autonomous agents to act like real human engineers, to plan things out, navigate these huge, complicated code bases, and run a whole series of tasks, all by themselves. But the real question is, are they any good at it? Like, really? And this, right here, this really gets to the heart of the problem. On the one hand, you have this friendly, simple idea of an AI coding assistant. But on the other hand, that's the reality. It's a complex, tangled command line world where actual software gets built. And bridging that gap, that's the real test. Which brings us to a huge problem. It turns out the way we've been testing these AI agents, it's just not keeping up. We're giving them the wrong kind of exam. I absolutely love this analogy because it hits the nail on the head. The old tests we were using, they're like taking a driver's test in a completely empty parking lot. Sure, you can prove you can turn the wheel, but it's sterile, it's isolated. Real software development, though, that's like trying to navigate downtown traffic in the middle of rush hour. It's messy, it's unpredictable, and you have to think 5 steps ahead. So, let's break down what's so wrong with these old tests. For starters, they focus on tiny, isolated tasks. Plus, a lot of them were built using code scraped from GitHub, which is the same code the AIs were trained on. It's kind of like giving a student the answer key before the final exam. They also don't tell you where the AI went wrong, and most importantly, they completely fail to test for any kind of long-term planning.
So, to fix this, a team of researchers said, all right, enough is enough. They decided to build a better gauntlet. A new kind of test that's tough, that's realistic, and that's a true obstacle course for these AIs.
And they call it LongCLI-Bench. This isn't just another quiz. It's a collection of 20 really complex long-form tasks that were handpicked from over 1,000 real-world assignments and workflows. The whole idea is to push these AI agents to their absolute limits in scenarios that actually feel like the real deal.
And you have to appreciate the work that went into this.
They specifically avoided GitHub, so no cheating. They wrote every requirement by hand, so everything was crystal clear. They built each test in its own little bubble, a Docker environment, so it's perfectly fair and reproducible every single time. And they created this really smart testing system to make sure the AI solution actually worked. This was a massive human effort to guarantee quality.
At its core, this whole benchmark is built on one simple, powerful rule that every single developer lives and breathes. And that rule is this: when you add a new feature, you have two jobs. Job one, make the new thing work. Job two, and this is just as important, don't break all the old stuff that was already working.
And LongCLI-Bench tests for exactly that. They use what they call a dual set protocol. So part one of the test asks, did you successfully do the new thing we ask you to do? But then part two comes in and asks, okay, but did you break anything else in the process? This is what we call regression testing, and it's a way more realistic measure of what it means to be a good engineer. All right, so the stage is set. We've got this tough, new, realistic test. We've got the most advanced, state-of-the-art AI models ready to go. So how did they do? Well, this is where things get really interesting.
Just take a look at these numbers. These are the heavy hitters we're talking about. Claude's latest model, a 16.7% pass rate. The powerful GPT-based models, 15%. And it goes down from there. The chart says it all. These are not high scores.
Let me just put this in perspective. Not a single one of these top-tier AI agents managed to break a 20% pass rate. Think about that. When faced with a truly complex, real-world engineering task, the best of the best failed more than 80% of the time.
And here's the real kicker. It's not like they almost finished and then stumbled at the very end. No. The data shows that most of these AIs failed very, very early in the process. They completely stalled out before they even got 30% of the way through the task. And that tells you something crucial. The real problem isn't just fixing one little bug, it's the high-level planning right from the start.
Okay, so this sounds pretty bad, right? Does this mean AI coding is a failure? Not at all. In fact, the researchers argue this isn't a story about failure. This is a story about a critical discovery. And it points to the future of how we're all going to build software. Because here is the single most important finding in the whole paper. While the AI agents really struggled on their own, their performance shot up when a human collaborated with them. When a person stepped in to provide a high-level plan or just gave some guidance along the way, the success rates jumped. And the researchers themselves put it perfectly. They said future research needs to focus on synergistic human-agent workflows. And that word, synergistic, is everything. It's not about building an AI that replaces a developer. It's about building one that works seamlessly with a developer.
And that leaves us with a really powerful thought to end on. This research suggests that maybe, just maybe, we've been asking the wrong question all along. The question isn't if AI is going to replace us. The real and frankly much more exciting question is how are we going to partner with these incredible new tools to build whatever comes next? Because it looks like the answer is together.
You ever ask your AI assistant a really simple question and you feel like you're watching it write an entire PhD thesis just to answer you? Or maybe you give it a really complex problem and the response you get back is, well, let's just say it's a little underwhelming. It's a super common problem, right? But what if I told you researchers may have just figured out how to teach an AI to think more like we do, to switch between those quick gut reactions and that deep, careful, slow thinking?
And that really is the central question, isn't it? Most AI agents today are kind of stuck in one gear. It's like they're either flooring it in fifth gear all the time, or they're permanently stuck in first. And as you can probably guess, that's just incredibly inefficient. And a lot of the time, it flat out doesn't work.
So let's really dig into this thinking problem, and more importantly, the fascinating new research coming out of Fudan University and Tencent that's looking to fix it for good. Okay, think about it like this. On one side, you've got the AI that's a chronic overthinker. It's using the power of a supercomputer to decide whether to, walk through an open door. It's a colossal waste of energy and time. But then on the other side, you've got the underthinker. Sure, it's fast, but if you ask it to do anything that requires even a tiny bit of planning, it completely falls apart. This stubborn, one-size-fits-all approach to thinking actually has a name. It's called cognitive rigidity. And honestly, it's one of the biggest hurdles we face in creating AI that's genuinely smart and adaptable.
And this chart right here, it shows you the problem perfectly. Take a look at the data for GRPO. That's a pretty standard AI training method. Even when it's supposed to be flexible, look what happens. It almost always defaults to its deepest, most resource-intensive level of thought. You can see it right there in that massive dark blue bar. It is completely stuck in overthinking mode, and that is a massive, massive waste. So if the old way is clearly not working, where do we look for a better model? Well, it turns out the answer is a whole lot closer than you might think. It's actually right here, inside our own heads. So the researchers, they turned to this classic theory from cognitive science called ACTR. And at its core, what ACTR says is that our brains are absolute masters at shifting mental gears. We can go from total autopilot mode, like when you're tying your shoes without even thinking about it, to full-on deep concentration mode when we're trying to solve a really tough puzzle. We do it all day, every day. And this is where it gets really cool. This was the big what-if moment. What if we could actually teach an AI to be a mental gear shifter, just like us? What if it could learn on its own to pick the perfect level of thought for any given moment? Well, that is precisely what these researchers have built. Let me introduce you to a system they call CoGrouter. You can almost think of CoGrouter as like a personal cognitive trainer for an AI. It's designed to teach the AI to be flexible, to pause at every single step of a task and ask itself, okay, for real, how much brain power do I actually need to use for this next step? So how does it all work under the hood? Well, CoGrouter basically gives the AI a brand new toolkit with 4 distinct thinking modes, ranging from these lightning-fast reflexes all the way up to deep strategic planning. First up, you've got level 1, instinctive response. This is the AI's gut reaction. It's fast thinking mode. It sees an open door. The next logical step is to walk through it. It's a no-brainer. Simple, fast, super efficient. Then at level 2, we step it up just a notch to situational awareness. Here, the AI takes a quick look around, it assesses the current situation, and it considers its most immediate options. It's a little more thoughtful, but it's still very, very quick. Now, level 3 is where things start to get really clever. Experience integration. This is where the AI starts to learn from its own actions, from its mistakes. It literally looks back at what it's already done during a task and uses that history to make a much smarter decision about what to do next. And finally, we have level 4, strategic planning. This is the AI's slow thinking mode. It's the inner chess master. It's all about simulating the future, weighing different possible outcomes, and planning several moves ahead. This mode is reserved for the really tough, complex problems. So, okay, we've got these 4 different thinking modes. That's great. But how in the world do you teach an AI to actually switch between them at the right time? Well, that is where the magic of the training process comes in. The researchers came up with this really clever 2-stage approach. So in stage 1, they teach the AI what each of the 4 thinking modes is. You can think of it like teaching a musician how to play 4 totally different instruments. Then, in the second stage, they teach the AI when to play each instrument. And that's where it learns to become a true cognitive maestro. So how does it know when to switch? It actually all comes down to a single word, confidence. The AI learns to pick the thinking mode that makes it the most confident in its next move. If a gut reaction feels right and its confidence is high, it just goes with it. But if it feels a bit uncertain, it'll automatically kick things up to a higher, deeper level of thought until it's sure it's making the right call. It's brilliant. But let's be real. All of this sounds amazing in a research paper, but does it actually work in practice? Well, the results are in, and folks, they are nothing short of spectacular. In a series of really challenging tests, we're talking notoriously difficult benchmarks like ALF World and Science World, CoGrouter achieved a stunning 82.3% success rate. Yeah, you heard that right, 82.3%. To put that in perspective, that is a whopping 40.3% better than one of the most powerful and well-known AI models on the entire planet, GPT-4o. This isn't just a small improvement, this is a massive leap forward. And honestly, here's the part that might be the most amazing. CoGrouter got these incredible results while being way, way more efficient. It used 62% less computational power, fewer tokens, than the older methods. So it's not just smarter, it's also cheaper and faster. It's literally the whole package. I mean, this chart just tells the whole story.
look at that bar for CoGrouter way over there on the left. It is just towering over the competition, including GPT-4o and that GRPO method we saw earlier that was stuck in its ways. This isn't just a tiny little tweak to an algorithm. This is a fundamentally new and better way for AI to think.
This really is a huge deal. By teaching an AI not just what to think, but how to think, how to be flexible and efficient, we're unlocking the potential for AI that can start tackling some of the world's most complex challenges. And that, of course, raises a pretty fascinating question. Now that we know AI can learn how to think, what should we teach it to think about next?